I'm Raj, solution architect in Hazelcast. I am not the CEO of Hazelcast, but the picture does look, CEO and all that. So I'm not. So this talk is about boosting similarity search with real-time stream processing. Well, why just only similarity search? But a lot of operations, analytics, intelligence can be boosted with real-time stream processing. So what is real-time stream processing, and what is real-time all about? Well, as we say in Hazelcast, it's all about seizing the opportunity at that moment or preventing something bad happening. So for example, when the customer is banking, while the customer is at the ATM, or when the customer is shopping, walking inside the shopping area, or when a fraudulent event is happening, or predicting a fraudulent event before it actually happens, before a process breaks, or when the traveler is traveling. So while if we are able to do everything while this is happening, and that's where Hazelcast encourages users and customers to look at that side. But then we have Hazelcast is known mostly as a cache, and then where does the real-time streaming bit come in? So would like to spend a few minutes on the platform architecture of Hazelcast and what it is made up of and what components. So in the middle, basically, this is showing Hazelcast, and thank you for this. This is working today. Yesterday it was not working. We call our platform as the Unified Real-Time Data Platform. Unified Real-Time Data Platform. It is unifying stream processing and a fast data store. And it's a data platform. So the fast data store is what you know already about Hazelcast, the cache. Stream processing is basically adding compute and the ability to act on data as it streams into Hazelcast. So now how does data stream into or not stream into and basically is batched into Hazelcast? So basically these are just example sources where we say data is streamed into maybe a Kafka topic or a SQL database, NoSQL database, a file, or just so many different type of ways in which data can stream in. I mean, you heard I'm a lot from telecom. Although Hazelcast primarily the customers are banking, but telecom is all about streaming. There's just so much data that happens when you put a phone down. A call data record is generated, so all that can be streamed in. And now, for example, we'll take a call data record, and a call data record, for example, streams in, and here you have this compute power which is now going to work with historical data to act upon something. Now, for example, in telecom, somebody may want to know that if I have X amount of failure or call failures over a certain threshold from a particular endpoint or a particular geography, then well, there is something wrong. Please raise a ticket. Now the question is that this is happening real time. So we are aggregating, collecting, acting on the data as it arrives on the platform and working on it at that moment. Those who are from telecom will realize these are systems built over many years, and actually it doesn't really work real time. A lot of the actions in telecom happen after the fact. But with platforms like Hazelcast, and telecoms do use them, I use them, we are able to deal with streaming data, and another stream of data could be the call events. As the call is going through, as the user is acting, pressing a button or something like that, those are call events, and those can be acted upon. So stream processing real time and taking advantage of data real time. The processing is distributed via DAG. Everyone does that, and because the data also resides on the same platform, there is near zero latency when a compute requires any sort of access to the data. The platform also comes with an SQL. Yesterday I had a session, it was all about SQL, where I was basically pulling data from Kafka using SQL, and then processing, enriching that data using the fast data store and pushing that data out into another Kafka stream. And I was doing all of that using SQL. Basically Hazelcast is an SQL engine. And then of course we talk about our availability and consistency model. People can choose, users can choose, they want to be available or they want to be consistent in the choice, in the event of catastrophic failure. And then there are other bits, there are ways to talk into the platform. So now another quick slide that just shows us the value of data increases, the opportunity to find new business increases as more real-time action is done as compared to batch, where we pull the data, we transform it, store it, analyze it, do it later. Streaming data, where is quite popular, transform, store, analyze, and so on. But then we are saying that when you read data, you transform it and then you act it as the data is with you, and then store it if you want to. So basically what we are advocating is do not store that data, then run aggregations on it. Well, run the aggregations as the data come in and then act on it. So and then add AI, ML, and all of that. Today we will look at two demos quickly. One is going to be about enriching a similarity search and see how Hazelcast can help. And another demo, rather code, we will look at how Hazelcast can call Python models and so on. Now switching to the topic of similarity search and enhancing that with Hazelcast. It's just a stream of slides that's just going to build up with similarity search, vector databases, data representation, as you know, is quite important. How you have your vector data, have your original data, unstructured data represented within your systems, within your vector database. It's important how you formulate your query, how you put your query items together, how, for example, in case of a similarity search, which distance metric are you going to use, what works best for that particular use case, the search itself, how to basically go about searching it, as the results come in, the ranking of those results, the retrieval mechanism. While all of this are very important for a similarity search, what a vector database will provide is an ability to store unstructured data that is text, audio, image, etc. And well, while we do have the unstructured data cannot just be put like that. It has to be converted into the embeddings, and the embedding models basically help convert these unstructured data to the vector model. And these vector embeddings are stored in the vector database. Of course, we then have the search models, choice of search models on these vector databases. But then what we want to say is that vector databases, well, one of the things that they lack is a many-to-many relationship representation, right? So they are not about structured data, they're quite about unstructured data. So the ability to correlate data is sort of challenging for a vector database, as an example. And then time decay. We don't want that data to be held, queried later, just because we are unable to formulate certain queries which are based on some structure that is not available, or not have the ability to query real time, right? So time decay is an important bit. So a real-time vector database is basically instant computation, on new and historical data, right? So this is an important bit that we talk where Hazelcast helps is new, streaming in data, historical, well, data which is already there, club it and act upon it, right? So this is one example we saw yesterday where I was generating some data, random data to a Kafka topic. That data was flowing through and then into Hazelcast, and then Hazelcast had some maps, structured data, which was then being merged, and the final merge result was going out to a sink. So new and historical data comparison, that is quite important for examples like fraud detection, and we'll have a look at that. So a typical vector database search will require in our case what we are going to see is a movies database encoded and then stored into the database, and then basically search for a movie with a description, and of course encode the search itself and then search within the vector database so that the vector database is able to pull out the data. But additionally, we will filter that data. We will within Hazelcast we will have a map data of casts and actors, casts and therefore a cast map and an actors map, and basically these are many to many related to movies, right? A movie can have has a cast, and and of course the actors can work in many movies. So we'll merge the two searches and produce the final result. And this is one demo that we will quickly look at. This demo is you can visit this GitHub link. It has the demo from yesterday, the project from yesterday, and the similarity search, right? It has the Jupyter notebook as well. So basically the idea here is to I've documented all that requires to be done. I had to document it for myself because this talk was supposed to be done by DevRel head of DevRel, Dr. Fawaz Ghali, but he couldn't make it, so it's me who's doing this for you. So I'm also learning all of these, and therefore I just wrote everything down. So the steps are here. Now let's do one thing. It says I have to do two things. First, I need to run a vector database. So point number 7, a vector database, we will use Quadrant as a vector database. So we will start up Quadrant in Docker, and I think it's up. And the step number 2 says start up Hazelcast. Now, how to install Hazelcast, how to set up Quadrant. Quadrant was easy, it was just Docker, is documented in that link. So here is, I start Hazelcast. Hazelcast is a distributed system. Not typically, the minimum number of nodes in Hazelcast is 3. In this case, only 1 is running, which is of course my own machine. We have seen users who run on 2, but please, if you are one of those open source users running on 2, don't do that. It's not meant for that. It's meant to be running at least on 3 nodes. Now what I'll do is that I'll start a Jupyter notebook here. I have all the Python setup, and everything is all done, saving time. Now we're going to look at this example of similarity search. There's some talk about the benefits of a vector database, what it can do, and then there is some talk about Hazelcast and what it can do, right? So I'm not going to go through that because I'm quite interested to show you the code. Now these are all steps on running Hazelcast, running Quadrant, installing the necessary Python libraries. They have all been installed, all the pip and everything has been done. So remember what we are going to do. We are going to query a vector database, Quadrant in this case, get the data out, and then further filter that data with additional attributes. So this is just importing certain stuff, then getting a sentence, this particular sentence transformer, and then here is the set of data these are basically movie titles hard coded here. So it's an array of movie data. So we're just going to do that and then have a quadrant instantiated, and then within that quadrant collection we will have the data being put in. So the data is now put in, and then what we will do is that we will encode the description of the movies and put it into the quadrant database, so that we have an embedding of all the textual data. Now then, this is a query. There's no point actually me running tuck. I'll just go through it because it's a Jupyter notebook. The result is already here. This is a query to basically query ramen noodles, right? And then I think we're going to get some results. In this case, there is ramen noodles. In another case, there will be, I think, something about cooking. Yeah, this is about cooking, and so on. So these are certain results that come out of the vector database. No Hazelcast at this point. Here is trying to filter, where we say, hey, vector database, can you just search with word count of more than 100? And because it's an attribute, you say, yeah, sure, I can do that. So it's able to now filter the data with only of those movies which have a word count higher than 100. It's printed here, right? So I'm not going to run this. It's pointless. The results are here. Now let's bring in Hazelcast. Now in this case, what we want to do is that we have the movies data with the ID, title, description, and the vote count. We already queried on that. But additionally, we have the cast, which is a many-to-many relationship table, movies and actors. And of course, we have the actors database. So now what we're going to do is we are going to insert cast and actors, example cast and actors, into Hazelcast and help filter our data by an actor name. And I think in this case, any actor that has the words AN or letters AN in their name. This is a bit I was explaining yesterday in Hazelcast. So again, these are not important. In Hazelcast, basically, if you want to create or query a table, piece of data, map, then you create a mapping. So this is creating the mapping to cast, and this is creating a mapping of actors, cast and actors. So it just creates that, and then we are going to have some random data, actors and cast, and then we are going to basically create a map of actors and cast, and we're going to put that data into the actors map and cast map. This way we have the data ready, and now we are going to do an example query where we already have the hits. This hits is variable that is coming from quadrant, and then basically filter that data further with the cast predicate, right? The cast predicate is basically saying that where is the AN thing? Yeah, the SQL like AN, the name has like AN, right? So this is the ability to filter by many-to-many joins, and here we are filtering. And so when this thing runs, we have the results coming out, and in this particular case, it's the same movie data. But further filtered, where the name has AN, like Dylan Wang. Right. So this was an example of ability to boost vector databases or such when you have a use case of data streaming in, and you want to be able to not be limited by the limitations of a embedded database. Now let's go back here. I have one more thing to show. So this is, we just looked at the demo, but here is an example of a slightly more involved example of how, for example, Hazelcast is used in a multi-version machine learning interface, whereby we have more than one machine learning, more than one ML model being executed by Hazelcast. Just a reminder, Hazelcast is a distributed system. You ask it to do anything, it will just do it in parallel. And so therefore is an example of fraud detection, a very common use case where a stream of data, for example, if you swipe a card while the customer is still at the point of sale, the data comes into, for example, Hazelcast, and that system, the card network, will execute 5 different ML models on Hazelcast, and then take a majority vote out of that to see if this is a fraudulent or a non-fraudulent transaction, right? So Hazelcast will do that, and of course use its in-memory storage and make it very fast. Now, it's all about being fast, being reliable, and I'm a customer-facing person. DevRel is not my thing. And I spend all the time with banks who are users and are basically using Hazelcast for such mission critical use case and so on. Here's another example, deployment example, whereby data as it is ingested, of course, multiple ingestion of that data, and then we have a Python VM running inside Hazelcast. Now, the previous example, we saw Hazelcast calling a ML model outside of the platform, and here within Hazelcast, so let's say that these are 2 nodes, right? So basically the Python VM is within the whole Hazelcast platform. All these confusing crisscrossing lines is a DAG, right, which basically is just taking a piece of code and distributing it. Now, what is a piece of code? What are we distributing here? So let's quickly look at that. I got 10 minutes. I tend to finish these quite early. It's Friday. It's probably the last session.
It is very interesting.
Oh, thank you. Right. So let's look at a piece of code. It is actually fraud detection. It was written by Dr. Ed from Hazelcast, and what is it doing? So it's Java. As a developer, you tend to write these code as sequential. That's how we like to do it. So as a developer, the developer will write these code. If you are a Java developer, this will look very similar to streams. So what we are doing is that this first bit is, without going into too much detail, is reading a Kafka topic. And yeah, Kafka topic. There are a number of stuff here. There's no point going into detail. And it is, sorry, press the wrong button. Okay. I almost swore on public forum. So this line basically says that we'll read the timestamp from the source, right? So these things, while it's easy, it's actually leads to a lot of ifs and buts. See, we have to deal with problems of source being sparse. How do we deal with that, right? Because or data coming out of sequence, because we work with use cases of around aggregation. We want to aggregate data. Now we say aggregate by the minute, but what if some data comes after the minute? So all that things are factored in, part of Hazelcast. But anyway, choice. These are choices made by developer. Local parallelism of 10. That means every Hazelcast node will have 10 readings. So generally you deal it with partition. Hazelcast also works partition. Partitioned is also partition. So is Kafka. You can try and match the partition to actually improve performance. Then here is a piece of code that is mapping, that is modifying the data. What it is doing is that the incoming data is a card transaction. It has very basic data. So before we actually call the ML model, we need to collect the inputs, right? So the machine learning model requires the input. So this is basically enriching the incoming card with the incoming card transaction with the merchant data, right? So this is basically getting tuple get value string, and then so this is the merchant map. So basically enhancing the merchant data, which is inside the card the card transaction. We have basically here one more line that is enhancing the customer information. This guy is here to put me under pressure. And then some filtering, we don't want empty data. Further basically map Java streams. This is basically calculating the distance. If where the customer lives, where the card was swiped, that's an input data, right? Further tuple, this is just collecting more data. Merchant category, just trying to get which category the merchant, where this was swiped, which category the merchant falls into. Gender, these are all input parameters to the machine learning model. So we're just pulling that data out. Remember, all this data doesn't come in the card when the card is swiped. And the biggest challenge, the customer is waiting. If we do not reply in overall few seconds, the customer pulls out another card. Who's that? Some job. Okay, what job? Some job. Age group. Whether the customer is rural, urban, and so on and so forth. Zip code and all that. And this is transaction hour code. It just goes on and on and on. And you see, that's a lot of data. This is a lot of data that is being pulled real time. Try pulling it from a database, you can't do that, right? It's not going to scale. So you're just pulling from Hazelcast at that moment. Transaction, it just doesn't end. Transaction of week. Finally, we call the fraud detection service. So fraud detection service in this particular case is ONNX, which is basically embedded model within Hazelcast, within Java. This was, of the two pictures we saw, this was the one where the ML was basically embedded, I think. So basically this is all ONNX code. You can run this code. This is a public repository. As an example, you can try this out, and the result of this is pushed out, and then we push out what we want to do with it, right? So once we are done, we sync the data, and the sync can be another map or Kafka and so on. So this is an example of Hazelcast performing real-time for card fraudulent use case. I think I can make a statement: 75% of world's credit card transaction goes through Hazelcast. So, I'm done. Okay, before I go, maybe if in case anyone missed out to take a note of this, is your final chance. Thank you.